This is an example problem from Chapter 4 on Newton's third law. Pause for a moment and read the question. So you can see that this is a problem that takes place far away from any other large, massive planets or anything, so we can ignore gravitational forces and we can focus just on the interactions between these two objects. So Newton's third law, it tells us this, that any time you have a force, there's always a pair force or an interaction force that goes with it. And so if we have a force that acts on an object 1 by some other object that causes it, object 2, then that's going to be equal in length but opposite direction of the force that acts back on 2 by object 1. And in this case, our two objects are an astronaut and a space shuttle or spacecraft. And so we can see that in this case, we're going to call that force the push force, and it's if we look at it closely here, it's a contact force. And these two objects are interacting. In one case, the astronaut pushes on the space shuttle in that direction. The reaction force is the space shuttle pushes back on the astronaut in that direction. All right, so let's go ahead and solve part A for this one here. To solve this, we can go ahead and treat this just like we would for any other problem using Newton's second law. And so we're going to go ahead and draw a free body diagram and figure out the forces that act first on the spacecraft and second on the astronaut. Okay, so let's focus on the picture. Right now we're going to focus just on the spacecraft, so we only want to know forces that act on it. Well, the only force that acts on the spacecraft right now is the push force on the spacecraft. That's what the first subscript means, and by the astronaut. We can totally ignore this other force because it doesn't act on the spacecraft. So let's go ahead and set this up. We're going to go ahead and make a data table, and we'll draw a free body diagram, and we'll fill out the data table. So in our picture, we've only identified one force that acts on the space shuttle, and that's the push force on the shuttle by the astronaut. And we're told it has a magnitude of 35 newtons. So the length of that arrow is going to be equal to 35 newtons. And that's the only force. So our free body diagram here is complete. Now we should draw the acceleration too on the side. Well, if there's only a single force on the space shuttle, then the acceleration of that space shuttle, it'll accelerate in the direction of that force, right? So there we go. And again, that is x only as well. So we can go ahead and write in our things, our stuff into the table here. So we've got one force. We've got the push on the space shuttle by the astronaut, and then separately we've got the acceleration of the space shuttle. This is a nice problem because we got no y component, so those are all 0. For the space shuttle, the push on the space shuttle by the astronaut, we're told that it has a magnitude of 35 newtons, and that's all in the positive x direction, so 35 newtons. And the x component of the space shuttle's acceleration, we're trying to figure that out. Go ahead and put this into Newton's second law. Mass of space shuttle times acceleration of space shuttle in the x direction. Notice these guys are always going to be the same when we're doing Newton's second law here. That's equal to the sum of all the forces that act on the space shuttle, and in this case in the x direction. Let's go ahead and plug these things in from our data table. So space shuttle's got a big mass, 11,000 kilograms. And the acceleration in the x direction, we don't know what it is. We'll leave it there. The forces, there's only one force in our sum, and it's equal to a positive 35 newtons. And now we need to solve for a sub x. So we're going to go ahead and divide by both sides, and we'll figure it out. Plugging this into the calculator, we end up getting a small acceleration of 0.003 meters per second squared of the space shuttle in the x direction, right? If you want the magnitude of that, of course, since it's just in the x direction, the magnitude is just the absolute value of that component, and that's going to be equal to the same thing in this case, right? As an aside, the units for newtons, remember, they are equal to kilograms, meters per second squared. When we divide that all by kilograms, we get the cancellation of the kilograms, and we get meters per second squared, units of acceleration, so we are happy with that. Now for part B, what we want to do is figure out what is the acceleration of the astronaut. So we go back to our picture here. Let's go ahead and erase some stuff and clean it up a little. So in this case, we are only focusing on the astronaut's acceleration, so we're going to ignore the spaceship and just focus on the astronaut. And we see that there's one force that acts on the astronaut. Again, we're ignoring gravity. We're far away from Earth or any other planet. And this is the only force that we have to deal with on this astronaut here. This acts on the space shuttle. We ignore this force. Let's go ahead and draw our free body diagram, make our data table, and solve for the astronaut's acceleration. So here's a free body diagram for the astronaut. This dot represents the astronaut, and there's only one force. It's the push force on the astronaut by the space shuttle. Now, Newton's second law tells us that the magnitude of this force is the same as the magnitude of its pair force, the push on the space shuttle by the astronaut, which we remember here was equal to 35 newtons, right? And so we can go ahead and put that to the picture. So let's go ahead and draw our axes here. In fact, this is only the x-axis we need to worry about. Nothing going on in y, right? And so the length of this guy here, P A sub s, just 35 newtons. And we're going to go ahead and, so for our vector here, got 0 for y, and we've got a negative, because all the magnitude goes in the minus x direction, minus 35 newtons, right? Let's do the astronaut's acceleration. Go ahead and draw our vector there near the free body diagram. Single force, it's going to cause the astronaut to accelerate in the same direction as that unbalanced force. And so in this case, we see again for the acceleration 0y component, and we don't know what this x component is, but we'll figure it out from Newton's second law. Same as before, mass of the astronaut multiplied by acceleration of the astronaut in the x direction is equal to the sum of the forces on the astronaut in the x direction. And if we want, we can do a little bit of a math here ahead of time, right? So A, acceleration, we can divide the whole side by the mass of the astronaut. And the sum of the forces here, it only includes one term, right? This is just the push force of the astronaut on the astronaut by the space shuttle in the x direction, right? Let's put our values in. So this is equal to minus 35 newtons from our table. The mass of the astronaut, if we remember, the astronaut's got a smaller mass. Here it is 92 kilograms, so we can go insert that into our equation. And we'll get an answer here. It's going to be this negative 0.39 meters per second squared. That's the x component of the astronaut's acceleration. If we want to get the magnitude of that, of course, since it's only got one component that's not 0, it's just the absolute value of that component. And in that case, we know it's going to be 0.39 meters per second squared. So here's what we got. Great. Okay, let's just check a couple things and compare these. So notice that what we found out about the Newton's third law here. We found out that the accelerations are different, but the forces were the same magnitude, opposite direction. In other words, in part A, we've got this tiny, tiny acceleration of the space shuttle, and in part B, a much larger acceleration of the astronaut. What's the difference? Well, it all comes down to the mass of the object. Mass resists change in motion, it resists acceleration, so the larger mass object is going to have a smaller value. The tinier mass object, it's not able to resist the change as much, it'll have a larger value. of your acceleration. Nonetheless, the push forces on the astronaut by the space shuttle and on the space shuttle by the astronaut, these are still the same. A lot of people will get confused and think that the acceleration should be the same. They're not, because again, Newton's second law tells us that the acceleration depends on two things. It depends on the net forces that act on the object, but also on the object's mass. So even if the forces, in this case, single force and the object are the same strength, the accelerations won't be the same if the masses are different. This is something that can be quite confusing when you first encounter it, so I just want to give you a few examples here. Consider, for example, something like a hammer striking a nail. It seems like the hammer's doing all of the hitting, all of the force, but according to Newton's second law, these two force arrows, both of these guys have the exact same strength, and in the opposite direction. So even though that the nail's taking the brunt of it, it pushes back just as hard on the head of the hammer as the hammer does on it. Some other examples. Imagine a fly hits your windshield while you're driving on the freeway. We might be tempted to say that the force on the fly was much bigger because the fly gets crushed, whereas really nothing happens to the car windshield. However, the forces are the same. It's a action-reaction pair, Newton's third law. The difference in effect is in the different masses of the two objects. And here's one more example. Imagine the gravitational attraction of the Earth pulling the moon to keep it in orbit. A lot of people might say that the pull on the moon by the Earth is much bigger than the pull on the Earth by the moon, right? In reality, actually, the Earth and the moon, they're an action-reaction pair. The moon is pulling just as hard on the Earth as the Earth pulls on it, in an opposite direction, right? Why does the Earth seem to be more stationary and the moon goes around in a circle? It's because the moon's mass is smaller than the Earth's mass, and so the same force has a smaller effect on the motion of the moon than it does on the Earth.